Ale pan mówi w stronę Małgosi, bo inaczej nie słychać mikrofonu.
That's not important.
Not changing, but improving. Improving.
Just joining. Good. Dobra zmiana. Good time. So from now on, he will also participate in organizing. Of course, the main person should speak to the microphone. No, the main person is still Katarzyna Zenger, who is running really this seminar, and who will be helping her to set up the schedule. Okay, so today we have Małgorzata Siudek, who will present us something which is connected with her PhD. She will be the first PhD in our center.
I hope so. Good morning. I would like to present my project about formation and evolution of stellar population based on the red passive galaxies observed up to redshift 1. This is the outline of my presentation, which is divided into parts. I will focus on my main project, and this is the main topic of this presentation. But let's start from the beginning. This is the color diagram at which we see different morphological types of galaxies observed in local universe. So
Could you explain what is on the axis?
these are colors. These are of galaxy. These are two filters. This is the difference in luminosity in two different filters. And we can.
And then the vertical?
This is also color, but these are two different filters. This is NUV minus R. So these two filters, NUV and R filter, and here are the observation in R and K filter, the difference in these two filters. And these are just astronomical filters that are focused on observation in one passband. So we divide.
Why there's such empty space on the left?
Because we observed just galaxies in this range of colors. Let's.
But we see something close to the origin of this coordinate system, whatever it is.
Yeah, but
the galaxies here, and they are not slightly up. What's special
that
about
here.
this? Since I have no focus idea what is this one axis and the other, the question is that it looks funny that there is some critical value of the value on the vertical axis. That for a small x-axis, whatever it is, there are no high y-axis.
So this is just a color, yes. So this is something that we use in astronomy, and because as we observed in some filters,
But there must be a physical reason.
Not a physical, I think this is due to some observations.
these are observations. So this is not. We have to.
Observations.
Yeah, that's what. So there is no. The reason is
There are no
unknown.
data. Yeah.
Yes, we don't have observation here.
There are galaxies, but there are no data.
But that's
in the
because
data.
clearly there are observations corresponding to the high value of the y-axis.
Yeah, that's why we.
So there's no question.
Yeah, that's why we say that that our structure of galaxies are in the shape of these. Yes, because we don't have any observation of galaxies here. Yeah.
But the question is that cannot be observation problem because whatever is on the y-axis, the high value on the y-axis are measurable. Because there are points which are
but for intermediate values of the
for some values.
For
So the
some
question
values.
is why you can measure the y-axis for a high x-axis and you can.
Okay, I will because of the properties of galaxies.
So what? But if this is a property of a galaxy, then
Because these galaxies doesn't exist. These galaxies doesn't exist because here we have blue young galaxies, and here we have old, and these are different galaxies, and we don't observe galaxies which are here.
So the y-axis
With,
is the age.
No.
Y-axis is the color.
This is a color.
And the x-axis.
This is a kind of luminosity of galaxies. This is
So particular combination of colors can be linked to age.
yes. From this such a diagram, we can divide. We can say something about the properties of galaxies. So, as we see, we have a lot of galaxies, but we distinguish two galaxy types: spiral galaxies, which consist of mainly of young blue stars with active star formation, and a group of elliptical galaxies, which is known as red and dead, while it consists of old stars and show no sign of star formation activity.
It is observational, so it bothers me why this pattern is so regular, that they are just...
This is observational because they just set up the instrument.
They just measure
regularly at these intervals. This
Just
has
measure up.
nothing. This has nothing to do with the real world. The galaxies are everywhere. The measurements are quantized, so to speak.
So like how?
In the database, there are.
No, but how can it be if color is a continuous variable?
Sure, but the measurement is done.
We just have three filters and combine observations in three filters. So how come that these points are so quantized?
Because we divided them into morphological types. Because here we are
so-called galaxy lattice.
here we also analyze, we show the change of the structure of the galaxies. Spiral, disc-shaped, and then we are moving on and classified up to these more spherical, elliptical galaxies.
Are just points.
Yeah, each
Because apparently we have some spiral or something else, but this is irrelevant, yeah?
yes. Okay.
The artist's concept.
But the process leading to the formation of the spiral and elliptical galaxies is still under debate. There exist radically different evolutionary paths explaining this structure. And the key question is how and when did stars form at elliptical galaxies? Did they form very rapidly at high redshift, or they assembled mass gradually at relatively low redshift? We do not know that because, of course, this is a very complex process, but the main problem is that we don't have observation of galaxy past history. We have quite detailed map of galaxies in local universe in the radius of 2 billion years, but there was nothing comparable at higher redshift. And the situation changed.
Billion, you mean 10 to
9. Yes. And the situation changed with recently completed ESO program Vipers, who delivered a detailed map of galaxies up to the redshift 1, so that we are able to trace the properties of galaxies over the last 8 billion years. So the question is, if we look at the universe as it was 8 billion years ago at redshift 1, are we going to see these red and dead galaxies, or they were just on the stage of the formation? And the answer is yes, we see. Thanks to Vipers, we know that these red passive galaxies are existing from redshift 0.5 up to redshift 1. So we know that they are there. And I want to go deeper. When I want to estimate when the stars in these galaxies were formed. And then, now I'm currently working on tracing the evolutionary paths leading to the formation of elliptical and spiral galaxies observed at the local universe. So, to select my red passive galaxies, I use an evolving cut in color distribution, which was discussed already by Fries et al. In 2014 on using Vipers data. I use this bimodality criterion because of high and stable completeness up to redshift 1, but this criterion has a high contamination above redshift 0.8. That's why I developed a system of additional cuts to ensure high quality sample. And this is the UV distribution. With blue, we have these red passive galaxies selected with this bimodality criterion, but I cut the final sample is with red. This is the high quality sample of 4,000 red passive galaxies in wide range of stellar masses observed up to redshift 1. So I have a large sample of red passive galaxies observed 8 billion years ago. So how I can estimate, how can I track the star formation history? Of course, I can use photometric data, but the most robust method is to obtain, to analyze the spectral lines. So in my work, I'm analyzing the D4000 and H-delta index. These are two features, these are two indicators of age, and D4000 is the ratio of narrow wavelength range where we observe the accumulation of ionized metal absorption lines in atmosphere of stars. And that's in young hot stars we have a lot of multiple ionized metals, and we observe that the D4000 is small, and in old stars which dominate elliptical galaxies, the D4000 is stronger.
Can I ask a question?
Yeah, of course.
Now I find understood what is D4000. But the galaxy consists mostly of the stars of the same age. I mean, if I have a galaxy, it is an enormous amount of stars. Right?
Yes.
So how can I attribute the property of a young of the star to the galaxy on average?
On average,
Yeah,
this
and
we are
how
saying
is
about.
sensible if there is some rule that galaxies because if
You have
there
to.
are all ages, that should be.
You have to remember.
Washed out statistically. It is enough. So that means that the galaxies are somehow one age.
We are just generalize this because we are talking about all stellar populations, and you have to remember that we are focused
There is no
on.
rule that the galaxy consists most of the stars of the same age. That was my question.
There's a rule that it was born at the same when the galaxy was formed.
Yeah, but that's enormous time when they are born. So
You know, and
the
this
question
is a very.
Is there a simple relation between the age of the star and the age of the galaxy?
No, you have to remember that this is still under the question because for red passive galaxies, one of the theory is speaking that all stars, all stellar population were formed during one single burst, yeah, and most of the stars were formed, and then the star formation was quenched. Yeah, all stars were formed very rapidly, suddenly, and then the star formation was quenched, and no new star were formed. But this is just one theory, yeah, and we have another that it was not so rapidly, but it's in red passive galaxies. The most probable scenario is that they were formed very rapidly, and then the star formation was quenched very fast.
But since we have many galaxies, is it possible that they were rapidly born, the star, that the galaxy was born in that part of the universe very rapidly, and eons afterwards it was born rapidly in the other galaxies somewhere else? That this rapid event happens only within the one galaxy, not in the whole universe?
We are here. It may be, but that's why we need to have a statistical significance sample, yes, and because we have to find it out. And
you assume that there's a relation between whatever, that there's a dominant age of stars in a given galaxy, but as far as I understand, observations sometimes support it and sometimes not, and that's a discussion what can ignite and what can quench formation of stars. Assume that two elliptical galaxies collide. Can it ignite again the formation of stars or not? There are.
I would like to eat something.
No, it's absolutely harmless. But this is why this research is done.
yes, that's why it's.
To find how the distribution of ages look in galaxies which were red 8 billion years ago. It is by no means obvious that this is the same as now.
So I present for the first time the so detailed analysis of H delta index because so far the H delta is not so detectable on single spectra, and also.
I have still a question to the previous slide. This absorption T4000 line. I mean, if you have this metals have to be synthesized, right? Created
Somehow.
in supernova explosions. So I would say that if the galaxy is young and there were not that many stars and not that many supernovas, then it's not that there is multiple ionization, but simply it's a metal poor environment, right?
No, there is a lot of multiple ionized metals, and
Well, if a absorption line, I mean, a lot of ionized metals would mean that you may have absorption, or just because they are ionized completely, right? That's
Yeah.
what you are saying.
yeah. As we can see, the H delta index is not detectable mostly on single spectra. So I developed a stacking procedure to increase signal to noise to measure the H delta index. And I co-add my spectra in 6 narrow redshift range and in 6 narrow stellar mass range, and here we see with different colors my stacked spectra, and we can see that that H delta and D4000 is changing, but also another features are changing, like for example these iron lines. But in this work I'm focused only on H delta and D4000, but we can see that there is a lot of more information from my stacked spectra which can be further investigated.
But at the first sight, these figures are almost the same, which is surprising, even though the C factor is quite different, the shape
is similar, yes, because they are all red passive galaxies, so they naturally are very, very similar. So, as I have my high quality stacked spectra, what can I do with them? So this is the relation of D4000 as a function of stellar mass. Each point corresponds to the measurement of D4000 on our one stacked spectrum, and we have also checked how this relation behave for galaxies observed at the local universe.
You know the stellar mass?
From luminosity we have modeled the spectral energy distribution, compared with models, and estimate the stellar mass.
You do not see individual stars, you just have the luminosity
of the whole galaxy.
And from the luminosity of the whole galaxy you can extract the mass?
Yes.
That is
Yes, this is done from spectral energy distribution modeling.
You do not even know how many stars.
Yeah, that's
if you just see luminosity.
But because but
So what is the
They measure the density of stars.
How can you measure the density?
Looking at the given region and counting how many are in the region.
But this is on an average.
Yeah, on average, yes.
So how do you extract the mass?
Jedną liczbę można na wiele sposobów podzielić.
So in that case, it's not the stellar mass was not calculated by Gosia, but it's one of the collaborator in Vipers, and it's done based on the modeling, the real measurements in different wavelength bands with theoretical models. So it's kind of have like the whole grid of different models for stellar population, and then you fit them together. But it was not done by Gosia, but it's the work done by other member of Vipers.
But it heavily depends on the model.
yes.
So it's a model-dependent mass.
Yes. This is not the measurement.
In the sense,
Yes,
they
but
have various models and they pick up one which
Yes, it's
Right.
absolutely nice. They pick up some-
yes, this is Bourgeois Charlotte.
So it's for Vipers we use the Bourgeois and Shadla models. They are synthetic spectra.
But they are generated from the real observations. So the base of these theoretical models are just the observation, also spectra. And this is a very common model used in such a kind of analysis. So especially in my work, I'm not really focused on the exact values of stellar masses. I'm just very interested in the differences. So this is the point that I don't. Of course, the stellar masses are very, very accurate, but in my project they are not so important. The values, just rather the differences in mass.
Is there some simple explanation why there are galaxies with different masses of stars? Because apparently, for various galaxies, the mass is different.
Yes, and we observed that red passive galaxies are more massive than spiral galaxies.
So how do you explain this?
Yes, yes, and we observed that red passive galaxies are more massive than spiral galaxies.
How do you explain this?
Yes, So we can see that yes. We can see that D4000 is increasing with stellar mass and is decreasing with higher redshift. The H delta index behave opposite, so H delta decrease with stellar mass and increase with higher redshift. And what does it mean? That means that stellar population are getting older with lower redshift, and this is what we expect because galaxies are getting older with cosmic time. This is quite natural. We also see getting old. We also see that most massive galaxies, the stars in more massive galaxies were formed earlier than in low massive galaxies, and this is the confirmation of the downsizing scenario, which states that the star formation moves to smaller and less massive galaxies with cosmic time. This is one of the scenarios how the stars were formed in red passive galaxies, and we show that yes, we also see it. And this is something what was already observed on the basis of the observation in local universe. But for the first time, we present that this relation doesn't change over the last 8 billion years ago. And moreover, for the first time, we show that these conclusions are are completely mirrored by H delta index. Moreover, if we by comparing this relation for redshift 1 and for local universe, we see that it doesn't evolve with time. And this is not what we expected, because if we look at the D4000 stellar age relation, the relation is steeper at lower D4000 and lower ages, so that we expect that this relation would be steeper at higher redshift. But we see that they are comparable, and this might be because of the progenitor bias, that the youngest red passive galaxies observed at local universe were just on the stage of the formation at higher redshift, so that they drop out of this sample. And here we have the combination of these two relations. We have the H delta as a function of D4000, and we can see that is very tight correlation. And here we have with ellipses marked transition mass, where the mass function of spiral and elliptical galaxies cross, so that we can see that the scatter in H delta index is significantly larger below this transition mass, and that say us that this group of galaxies is not so homogeneous. They also have this youngest red passive galaxies which just joined the population, and above this stellar transition mass we have galaxies which are already in a state of passive evolution. Of course, this also says that low mass galaxies are populated by younger stars. So how to go to the ages of this stellar population. To estimate the age, we can compare with theoretical models, and I have derived the relation of D4000 and H delta as a function of stellar age for Bruzal and Charlotte models, which were already used for vapors data to estimate stellar masses, and from comparison of our measurements of D4000 and H delta with models, we can derive the epoch of the last starburst. And
how do you generate these synthetic galaxies?
Because I have some theoretical models and giving me some input parameters, what kind of stellar population I'm expecting, I can see how.
You generate artificial database.
Artificial spectra, which I can measure my spectral lines.
But this artificial spectra require a certain model.
It's like a multi-tabulator.
So they were based on the observation in the
But the Monte Carlo, I mean, you have to specify the energy, or the function. You have to know.
Łukasz, you have there is some physics which you understand. You agree with that or not? Like nuclear physics, low energy nuclear physics. So stellar processes. I remind you that neutrino mass was discovered because of the difference between observation of neutrino flux and so on. So you then apply this to evolution of stars. Now you add many stars and form a galaxy, mainly under the influence of gravitation, which we somehow, I think, also understand on the galaxy length scale pretty well, right? Then you calibrate those models on the local universe and make them whatever we can, when we can distinguish single stars in telescopes, measure single star spectral lines, and so on, so on, so on. And then you apply it to this situation. There is nothing better we can do. I mean, maybe there is, but the floor is open for a better idea of how we can analyze this data. We just have technical possibilities to measure spectra far, far, far away, long, long time ago, and here are those spectra, and now we need some physics to interpret them, and the only physics we have is the same physics as we have produced and calibrated in the local universe.
So, as we can see, this relation are not only dependent on the age, but there is also a strong dependence of metallicity, where each color corresponds to different metallicity. So we know that the stellar metallicity doesn't evolve with redshift, but change with stellar mass, and Galaxy et al. 2014 has found that this metallicity is slightly above solar metallicity for high mass red passive galaxies, and we have also verified this relation for galaxies observed in local universe, and we have the same conclusions. So and also for the first time we find out that the relation of D4000 as a function of mass is changing due to variation in age and metallicity on the equal level in red passive galaxies, of course. So by comparison with models, we estimate the redshift of formation, and we can see that redshift of formation is increasing with stellar mass, both from measurements on D4000 and H delta index. We also see that redshift of formation is increasing with redshift, what give us the confirmation of the progenitor bias. And this also means that the true evolutionary track of red passive galaxies may be underestimated when we look at the low redshift. So we have I have created a consistent picture of redshift of formation as a function of stellar mass with red squares. We have the measurement with D4000, and with open diamonds we have estimation of redshift of formation obtained from H delta index analysis. And for the first time we derived such a picture in so wide stellar mass range, because the previous results were focused rather on very narrow stellar mass ranges. So just to give the summary of my main project, which is already completed, and the results will be published in this year, we have found red passive galaxies at redshift 1. We have selected a wide sample of 4,000 galaxies. We show how the D4000 and H delta behave as a function of stellar mass and redshift, and we create a consistent picture of the redshift of formation as a function of stellar mass. This is very nice work, because for the first time we do such an analysis beyond the local universe with such a statistically significant sample. We show for the first time the so detailed analysis of H delta index as a function of stellar mass and redshift, and we present and we estimate the redshift of formation, which show consistent results with previous one. Of course, all the results were presented on two independent measurement of H delta and D4000 and give consistent results. Now I would like to present my project that I'm currently working now, which is focused on tracing the evolutionary path leading to the formation of spiral and elliptical galaxies observed at local universe. So the question is how we can distinguish different types of galaxies at redshift 1. This is work done by, this is the same color diagram that I that was on the first slide. This is the color diagram for Viper's data done by Fries et al. 2014, who has found elliptical galaxies and spiral galaxies in Viper's dataset. 2 years later, Davidson, on the same color diagram, tried to distinguish third group of intermediate galaxies. And now we are forgetting about that and try new approach, and we use unsupervised classification based on the multidimensional absolute magnitude space, and using no training sample or any hints, our classificator divide our Viper data set into 12 classes, which are well separated on the same color diagram. So we can see that in spiral galaxies we see additional structures in also in intermediate and also in these red passive galaxies. We can see that our physical, morphological and spectral properties are changing from class to class, going from blue spiral galaxies to red. Our galaxies become more compact, more red, are more massive, and also from this is D4000, they become older. So we can see that our classificator is tracking some evolution in this evolution pattern in these galaxies. And we can see also the differences in spectra, where blue spectra have lines in emission, and when going to the redder, older elliptical galaxies, lines are in absorption. So how this changed with cosmic time? Maybe you will guess. This is this color diagram at redshift 0.5, and now we are going back to the past. And do you see any differences? What has changed?
Something has changed.
Yes, for our example.
Not too much.
Yes, but some change we can see. For example, look at this group, which I'm particularly interested of red passive galaxies. Yes, of red passive galaxies here. So we can see that they are quite well distinguished. And now something about 0.7. These two groups are together. Yeah.
Well, the big question, of course, is what are the error bars? I mean, how accurate are these ellipses? Because that could be so that there is no difference because you are within the error bars.
Yeah, these ellipses. So the center is the median of the color for this group, and the error is the first and third quartile.
But what is the error bar?
This shape of the ellipse. This is the error.
Yes.
Yes.
But what?
This is the quartiles of my.
I understand the shape,
Uh-huh.
but the question is from observations. You have statistical data, and there are statistical errors, and they give you some error bars on these results.
So is this tricky for
What is the error bar as compared to the size of this ellipse? Because if the error bar is of the same order, then the change is insignificant.
It's very small from the
Yes.
from the instrument we observe the galaxies. It's 0.05 magnitudes for one band, so in total
It's negligible.
It's not visible on the plot.
Okay.
But maybe it's a different question because I understand that error bars of measurement for a single galaxy is very small. However, there is some distribution within each
Yes,
population. And what is
statistical error.
how wide is this distribution? So I understood from presentation that this is like 4 or 3 sigma in distribution, right?
Yes.
Values. Okay.
So I tried to investigate the redshift of formation for these red passive galaxies, three different classes, and we can see that at lower redshift, the redshift of formation change a little bit from class to class, while around redshift 0.8, these two groups, we don't see any separation. Of course, these are very preliminary results because I'm just currently working on this, and this is what I would like to focus on in my analysis now. Also to investigate more how these stars were formed in red massive galaxies. I'm introducing to my studies not only the analysis of spectra, but I take into account the photometry and try to model the spectral energy distribution of these galaxies. And just to summarize, we develop a new classification which which separate our galaxies into 12 different classes, which follow the evolutionary path from blue star forming to red passive galaxies, and we may find a more detailed picture of the evolution, and I would like to focus on analysis of this group of red passive galaxies. And that's it. Thank you.
A naive view for a person who is not very well informed like myself, there are elliptical galaxies and there are spiral galaxies, and they look completely different.
Mm-hmm.
But I understand that there is a continuous
Path.
change, that there are elliptical that evolve into, that have some arms, right? But they're still elliptical.
Yes.
On the other hand, you have typical spiral galaxies. But when one looks at various nice pictures of galaxies, I have never seen something that would really be in between. One shows these pictures from Hubble and
Because they don't look like
observations.
nice.
Yeah, maybe that's the reason.
That's the reason they don't like.
But there is a continuous spectrum, right? You can connect the elliptical galaxies
So you
with the
mean the
spiral
elliptical galaxies are also.
Yes, we believe in that, and that's why I try to, because it's under debate how to find out this path going from spiral to elliptical. Yeah, so it's very hard question, and we don't know how this process was, how to find this path. That's why I'm trying to find some classification that allow us to track the steps going from spiral to elliptical galaxies.
Models which can tell why some galaxies are elliptical and some spiral.
angular momentum.
Yeah, of course.
That's the only.
I can have the elliptical object which also rotates. Why
But it will
not?
not, if it does not have arms, as we know, angular momentum
Yeah,
depends.
I know this will sound very strange.
There is
But if
apparently
you-
some
yeah,
mechanism if it
Yeah, if you
rotates.
there's some kind of interaction within this thing, collision.
It's a kind of wave propagating.
Or wave or I mean, but the elliptic, you can take a silly putty out of the toy stores and rotate it,
There will be some angular momentum, but
and there will be still elliptical and will not form the kind of spiral structure. And if you have in the T leaves, and if you rotate it, that will form kind of a spiral, right? Because the mechanism is different.
We have an ellipsoid, and if it is a rigid body, then you make rotate it, but this is not like the
Yeah, it
angular
may-
momentum.
right.
It may not be rigid, it may get flattened or may
There is
get more.
some-
I mean, you may build
But
a
it's not-
Small region with angular momentum, it starts
But
to.
it does look like some kind of a phase transition that these arms develop. Some kind of instability.
So, but the instability must have you break something.
Yes, that's right.
Some either break interaction or some symmetry. So the question is,
The Vipers and what has been collected in the local universe, such that we avoid these models, but just compare kind of features of spectral lines or
True data.
true data to true data.
Yes, of course. So
fit-
it was
the fit
something
the
that
data,
Gosia did at the
micro
beginning.
data.
So she measured for different spectral features. But then if you want to say something about the age of the stellar population, you need to use
Sure.
models. So for example, you need to assume the age of the universe, for example. So we need to, so we can say something about the relation, the slopes of the relation, but if you want to give a number, you need to connect to the models.
Okay, so let us assume that we allow for cosmological models, right? So we know what is a redshift, basically, because without that,
Yeah.
it's
Yes.
hard to say. But we still want to avoid specific model for stellar evolution or this relation between luminosity and mass.
So you want to fit the
So what can be done then? Is it possible to